Hello, everybody. This is for the course at UNSW for MATH2099. I'm going to solve the question 13, and it is related with the subspaces. So we are going to use subspace theorem to solve these exercises. First of all, I would like to recall informations or the context about the vector spaces. And this is how this is my perspective, and this is not a lecturing. So you must have a proper definition in your lecture notes and in your books. This is just a reminding yourselves what is the structure looks like and how we approach. So when we say V is a vector space over a field, maybe I will be good if I enlarge it. Myself here. Okay, we have a vector space over a field. So you have a set, and this is usually the infinite set in your level, but it's not necessarily infinite. There are some finite vector spaces. And over a field F, this is a field structure. A field means you have multiplication and you have addition, and a field is has very nice properties related with the additions and multiplication. And when you think about a field is the best example that you can think of in the real numbers, rational numbers, complex numbers. But know that a set of integers are not the field, because you don't have inverses for every element with respect to the multiplication. Okay, now you have a vector space. That's what we are going to define. That's what we worked on. You worked on last year, actually. So this is really the reminding of ourselves. So we have an addition and we have scalar multiplication. We have two operations defined in vector space in that set. And we would like to have for V set and the addition. So this addition related to elements of the V. And we want certain properties satisfied with respect to this operation addition. So addition is only for the vector spaces, but we know that we have another additions for the fields. And we usually actually use the properties of the field to prove the properties of the vector spaces. Anyway, so this is we want to, this structure, having these properties, we call it the group structure. So the vector V, together with the addition, we must have closure, associativity, identity. This identity with respect to the addition, it means that you have a zero. And the inverse with respect to the addition means is the negativity. You have negatives, you have minus V. If you have a vector V, you have minus V. If you add V with minus V, you will have the zero vector. So zero vector exists in your vector space, and this is the group structure. And then you have the multiplication. The multiplication is not the elements of the two elements of the V. Multiplication is the one element from the V, another element from the field. So we can look at the scalar multiplication like the field acting on the vector space, acting on the V. And we have three properties needs to be satisfied with respect to that. This is why I'm grouping it. This is only inside V. This is the V F acts on V. So we must have the closures with respect to scalar multiplication, association. And the one is the identity, multiplicative identity of the field. And it affects the vector spaces as identities or trivial. It means that 1 times V is equal to V. Does not affect. So these are the properties part of the vector spaces. And then since you have one addition and one multiplication, you want the associativity, you want them to compatible. Some conditions on compatibility is necessary to be able to work on this, on the set. So scalar distribution and vector distributions are the compatibility conditions between V and F. Or another way of saying is that's a compatibility condition for addition and scalar multiplication. So this is the structure of the vector spaces, right? And now subspace. You have a subset and you have a vector space. So V is a vector space and you're thinking in a subset. And if that subset satisfies certain condition, then we call it a subspace. Or if subset is a vector space, we call it subspace. So if we know that we have a bigger set is a vector space, it is easier to prove that the subset is a vector space, or another way of saying it, subspace. We are going to use a subspace theorem for it. So as we know, we don't need to go through all these 10 axioms. We don't need to go through these 10 axioms. We will only check 3 axioms if they know that there exists a bigger vector space as a well-known vector space. In that case, we need to check 3 properties. 0 needs to be inside that set. And if you have any 2 vectors in the set, when we add, it should be in the set. So this is the closure of the addition. And this is the closure of the scalar multiplication. So lambda is from the field and the vector from the set. And when we multiply lambda times u must be S. So 0 needs to be in the subset. It must be closed under addition. It must be closed under scalar multiplication. And some, if you look at some definitions, some books does this definition. So these 2 property is equivalent to this property. It's exactly the scalar multiplications. It's a combined closure of the scalar multiplication and the addition implies this. So this property is equivalent to this property. You can use this one or you can use this one, whatever you like. If you use this one, so you have to prove 2 axioms. If you use this one, you can do it in 1 line. Whatever it's clear for you is perfectly fine. Okay, now I'm going to go through the solutions of the question 13 to practice the subspace concept. Okay, the first questions, the question 13 means are the following sets are the vector spaces? That's what we are going to check. The first question is consist of the sum vectors in R3 satisfying this condition. It's called this set S. So S is in the subspace, subset of R3. This is the only thing that we know. And R3 is a vector space over the real numbers. So this is a 3-dimensional Euclidean space that we always work it out. This is well-known fact. This is a vector space. So in order to prove that S is a vector space, we only need to prove that S is a subspace of R3. That's what we need to do. So if a 0 vector is inside the S, because if you put 0, 0, 0, that will be 0. So the 0 vector is in this set S. The second property, we want 2 vectors in the set S, any 2 vectors. This means for all X and Y in S. Then with respect to this decision, we have 2 conditions. There's one with respect to X, there's one with respect to Y. I realized that I need to. This is supposed to be Y2. This is just writing Y2, Y3. And then, so we have these 2 as X and Y vectors are in the set S. So if we add these 2 equations and simplify the equation, collect the 2, then we will have 2x1, y1 minus 3x2, y2 plus 3x3, y3 is equal to 0. But this equation means that this vector here is in S. So for any 2 vectors, the addition is inside S. S is closed under addition. Then if we have any vector in S, then it has to satisfy the equation. By multiplying this equation by any element in the field and simplifying, which means that we are multiplying lambda, and since lambda is a scalar, 2 is a scalar, they're all scalar. So when we multiply this equation by lambda, you are already inside the field F. And we in the field F, lambda commutes with 2 and x1 because they're all real numbers. Well, the F here for us is the real numbers, right? I don't need to say F anymore. Okay, and then this equation, by multiplying lambda, we will have this equation which says that this is the first component, second component, third component. That was the equation. It means that this vector is inside of S. So S is closed under scalar multiplication. Therefore, S is a space, is a subspace of R3, and particularly S is a vector space by the definition of a subspace. I think this is clear. Let's give us some contrary example, that is the part B. If you have the vectors in R3 satisfying this kind of equation, the zero vector is not in this set. And immediately we understand S cannot be a subspace. And so it cannot be a vector space. So that's that simple. We only need one contrary example for disproving something. So that's what we do. So the second one is also a contrary example, but it's not that obvious. Let's do that. So we have the vectors x1, x2, x3 in R3 satisfying this equation. Now, zero vector is in this set S, because when we put 0, then 0 is smaller than or equal to 6, which satisfies, so the zero vector is in the S. But we are going to see that S is not closed under addition. Let's see, do that. If x and y, any two vectors in this set S, then it satisfies this equation and satisfies this equation. If you add those two equations, we will have this inequality because you're adding this one, 12. And this doesn't mean that this inequality is smaller than or equal to 6. It does not need to be, because this condition and this condition implies this inequality does not imply smaller than or equal to 6. You can give an contrary example if you wish to, but it's enough to say that these equations needs not to be satisfied. And that does not imply that x plus y is an S. So S is not a subspace. So S is not a vector space. It satisfies the first axiom, but it doesn't satisfy the second axiom. Okay, let's move on. You can also use the third axiom as well. That would not work. But once you realize that something fails, you don't need to go through anything else. Okay, this is an example, and let's see how we will work it out. So this is the set of the polynomials satisfying this condition. Now, remind ourselves what was P3. P3 were all polynomials of degree smaller than or equal to 3. If you want to write it down this vector space, and we know that this is a vector space over the real numbers, and this is a well-known vector space, we've studied last year a lot of this vector space. So A0 plus A1x plus A2x squared plus A3x cubed is AI's are real numbers, and I is 1, 2, 3. So these are the polynomials of degree 3 and less than 3. It could be A3, 0, then you have the second order polynomial and so on. So this is a vector space. So S is a subset of P3. Only in order to be able to see that S is a vector space, we need to prove that S is a subspace of P3. Now, remind ourselves what was the zero element in P3. Zero element in P3 is defined as the zero polynomial. That is z of x is equal to 0 for all x in R. Right? So it means that A0, A1, A2, A3, for all of them 0 at the same time. This is the view. For all x, it will be 0, or it's just a 0. But this is the definition. So 0 polynomial means a polynomial, in this case, is a polynomial of degree less than or equal to 3, such that zx is equal to 0 for all x. This is the definition. This is a very common mistake that the student does, but this is the full definition. It's not only the 0. That is the 0 polynomial. That is the 0 element in P3. 0 is a number, but the elements of P3 are polynomials. They are different concepts. Right? So 0, only looking at saying this 0 as 0 is incorrect, because 0 is a real number, and as a real number is not really polynomial. As a conceptually that we approach that way. So 0 polynomial, when we take the derivative, it's also 0 for all x's. And then it satisfies this condition automatically because 0, 0, 0. So it satisfies this condition. It means that the 0 polynomial is inside S. So it satisfies the first condition. Now, second axiom says that to take any two vectors in your subset. In this case, it will be two polynomials in this set. Since this two polynomial is in this set, it has to satisfy this condition. For Q is an element of S, should satisfy this condition. Now, from that condition, we need to we need to look at the axiom for P plus Q. We want to prove that P plus Q is in the set S. In order to be able to get that, let's start from these two equations, add these two equations, and try to simplify. If you add it, we have this equation. And this equation is not good enough. We got to do more, because this equation does not say that P plus Q satisfies this property. This property x times polynomial derivation equals to 2 times the polynomial. So P plus Q is the polynomial that we would like to obtain or hold this equality. Right? So this is not enough because I don't have P plus Q cases here. But in P3, we know that P prime plus Q prime X is equal to P prime X plus Q prime X, right? This is the simple rule for the derivation and applies to all polynomials. And also we have P plus Qx is equal to Px plus Qx. As you see, I can replace this one with P plus Qx. I can replace this part with the P prime Q prime X. Then I will obtain this equation. Now I can say that P plus Q is an S, because that satisfies that. Probably I should have wrote down one more thing here, like saying that P plus Q derivation. I missed a simple. This is a P plus Q derivation. I think it is better to take this one in here. There's an XE here. There's an XE here. And that is a prime. So this one, P plus Q satisfies the equations like this. X did a polynomial derivation is equal to 2 times the polynomial X. Polynomial derivation, 2 times the polynomial. This implies P plus Q is in S. Okay, so S is closed under addition. So the last axiom that we would like to show is that the S is closed under scalar multiplication. For scalar multiplication, we want an element from S and an element from the field. In this case, is the real numbers. Since P is in S, it needs to satisfy this equation. Multiplying by any lambda in R gives us this equality, just multiplying lambda. And lambda is a real number. These are the real numbers by using the polynomial properties or the real numbers multiplication. So real numbers with respect to the multiplication is commutative. I can't move this lambda here. So this is not good enough still because it is not in this format, right? X times the polynomial derivative. This will not imply that lambda P is in because I need to do something here. But we know that for any lambda, for any real number, we have this property, lambda times any polynomial derivation can be written as a lambda times P derivation P prime, which means that the constant will not affect, multiplications by a constant will not affect the polynomial derivation. And using this fact, now I can rewrite this equality saying that x lambda p prime x to lambda p x. Then, since this is x, polynomial prime to polynomial x, so this is a polynomial inside S. So scalar multiplication is closed in the set S. S is closed under scalar multiplication. Okay, then we prove all these three axioms. Then we would be able to say that S is a subspace of the real numbers, and it is a vector space because every subspace is a vector space. I hope this is clear for you. Let's do the last example. That is the most interesting one among this question, actually, these exercises. Here we have a matrix. This is the matrix 2 by 3 over the real numbers. And AX is equal to XB. Now, A is the matrix 2 by 2 matrix, and B is a 3 by 3 matrix, and they are fixed. A is a fixed matrix, B is a fixed matrix of this size. And satisfying this condition, we are thinking about all matrices of size 2 times 3, satisfying this condition for a fixed A and fixed B. So that's the set S. Let's think about it for a while. Is this legitimate? Is this logical? So A is 2 by 2, X is 2 by 3, X is 2 by 3, B is 3 by 3. So we can multiply this because this is equal to that number. The columns of the A is equal to number of the rows in X. So we can multiply this. And when we multiply, we will have a matrix of size 2 times 3. Here we have 2 by 3 matrix for X, and the B matrix is a square matrix 3 by 3. And this number is equal to that number. Column number of X is equal to row number of B. So we can multiply this to a matrix, and the result will be 2 times 3. So this is logical, right? As a matrix multiplication, this is logical. So that's the situation, and we would like to show that. We don't know in the beginning, but we would like to go through all these axioms, and we would like to see whether S is a subspace or not, or a vector space or not. Go through the, so 2, 3, all matrices of the size, in a certain size, any size, is a vector space over the real numbers. These are all matrices over the real numbers, so any size, like Mn, it will be is a vector space over the real numbers. This is a fact. So S is a set, S is a subset of M23, which is a vector space. So we can apply the subspace theorem to see whether it is a vector space or not. So the 0 is inside because think about the 0 matrix. The consist of all entries are the zeros of the size 2 times 3. A is a fixed matrix, B is a fixed matrix, but if you multiply it with 0, it's always 0. So both sides will be the 0 matrix in a different size. right? This will be 2 times 3, this will be 2 times 3, but it doesn't matter. So this will be equal because everything will go to 0. This is the 0, 2 by 3, 0. Right? That's, I think it is clear for you. So this 0 is inside of S. Now, the 0 element of the bigger vector space is inside your set, is inside your subset. Good, that's tick. Now the second axiom, we get 2 matrices, 2 elements in this S. And we would like to prove that the addition is inside S, closed under addition. That's what we would like to check now. Since these are elements in S, it satisfies AX is equal to XB, and Y is in S, so this equation holds, this matrix equation holds. AY is equal to YB. Since we are interested in X plus Y, it is logical to add these two equations and try to see. So if you add these two equations, we have AX, AY, XB, YB. We can apply the distribution law of the matrices. That will be A, because A is common. A will go out. If it is a multiplication, you can't do that. Right? I mean, if you have this multiplication here, since this is an addition, I can do this, right? I can take this A outside. I can do that in matrices. That's what I'm trying to say. And also I can do B outside because this is an addition here. Consolation law, it does not work for the multiplications over the matrices. That was, I was trying to make a point. Okay. And then, since this, it looks like it satisfies this equation, A times the matrix is equal to the matrix times B. That's that one. A times the matrix times B. It satisfies this equation we found. It means that X plus Y should be inside S. So the third axiom, we will have an element. We will just take any element in S. You cannot take a particular element. You are proving something, so it has to be any element in S. Then it holds that AX is equal to XB by the definition of S. For any lambda in R, we just multiply this by lambda. Lambda is scalar. A and X are matrices. If you have a scalar multiplying by matrices, it means that you're multiplying every entry by this scalar lambda, right? And then you can, lambda is a scalar multiplication over the matrices, you can move, right? You can, matrix multiplication is not commutative, but if you have only one lambda multiplying the matrices, you can commute that. Only this scalar multiplication commutes actually inside the matrices. So this is why I can take the lambda here and lambda here. So that will allow me to say that lambda X is inside the subset S. So that proves all these three axioms holds. Then S is a subspace. So in particularly, S is a vector space over R. That's all for I would like to say in this video. I hope it is useful for you. I hope we remind you for the last year's concept about subspaces and subspace theorem. Thank you very much for watching it. Thanks.